going to talk to you about Space Forge. We're a relatively new player on the scene. Give you a bit of an introduction in terms of what we're doing and why. I thought I'd start off straight away. The title Space Forge suggests we're a space company. We're actually an advanced materials company with the idea that we're going to leverage the conditions of space to produce these advanced materials. And what I'll do is talk through how we're aiming to achieve and realize that, what some of the underpinning science is, what some of the materials are that we're working on. And also, I've started off by saying we're not space, we're advanced materials. First half of the presentation is going to be about space activity, so don't want to confuse you too much. But the company was set up in 2018, and it was set up by a couple of lads, Josh and Andy, that used to work for Thales Alenia Space. So it's really come from the space sector, and they were able to see how the space industry is rapidly evolving, moving away from the sort of state-funded activities to more commercial ventures and activities. And they identified that there was an opportunity to really lead the way with looking at manufacturing of materials in space. And when I say materials, there's been numerous experiments on alloys, pharmaceuticals, and semiconductors. They chose to work on semiconductor area. So really sort of ticking those two strategic, highly valuable national sectors of space and semiconductors. So we're based in Cardiff. That's where the sort of manufacturing HQ is. We've got offices in the US to tap into the US semiconductor and space industries and funding streams. And we've opened an office in Portugal. And the Portugal office is it's in the Azores. And there's a great big, nice piece of Atlantic Ocean where we can return our satellites to. And I'll talk about that later. We've got over 70 employees across 20 nationalities. So we've grown relatively quite quick. The company was sort of birthed during COVID, so there's a lot of us that are remote workers. We recently raised quite an eye-watering sum in terms of Series A funding that was led by the NATO Innovation Fund. But as you might expect, operating in both space and semiconductors, they're not cheap industries, are they? In 2023, we launched a proof of concept satellite. It was a small CubeSat. It went on the Virgin basically, it was on the Virgin launcher, and I want to say it went up into space. It ended up at the bottom of the sea. It wasn't our fault. But this year, we got a UK license from the CAA to launch a satellite into space for advanced manufacturing. And that is actually quite an achievement. There's no real regulation or legal bodies looking at any of this in any, or there's no history or frameworks in place. So there's a lot of regulatory hurdles to overcome with what we're doing as much as technology. And this year, we've launched Airforge Star 1. So just to give a bit of an overview on that. So we assembled it in Cardiff, transported it out to the States, it was integrated into the launch vehicle. That's our team over in California. and it was mounted onto the Falcon 9 rocket, along with 70 other satellites. Oh, no. There we go. And this is what happened.
T minus 15 seconds. 10, 9,
Everyone knows
8,
it's a good countdown.
7, 6, 5, 4, 3, 2, 1. Ignition. And liftoff of Falcon 9. Go SpaceX, go Transporter 14.
So that was super, super excited. Super exciting. It happened just after IMS in San Francisco. I didn't realize it was actually happening because I was more focused on the semiconductor side of things, so came home before watching the launch. But yeah, just to prove that we did make it up there, we've got a photo of our satellite, on board our satellite, up in space. I don't know if that's the sun or the moon. Sorry if they're both very, very shiny up there. But yeah, it's been up there going through a whole heap of commissioning. And I think that, I've mentioned that there are 70 satellites on board. To try and pick out your satellite when there's 70 just being dropped off. It's quite a challenge. Identify it, communicate with it, orientate it, get it to start operating. And so, as much as anything else, this is just sort of demonstration that we've been doing that from our SatOps room. So, we've got a prototype satellite up in orbit with a prototype payload that we plan to do some initial experiments. But the overall sort of business model for us is that we do build our own satellites. We launch them. So within that satellite, there is the payload. Crucially, we deorbit it, control deorbit, return it back to Earth. And as I mentioned about, there's always find appropriate landing zones that we can then recover, take the payload out, the materials out, and then the intention is refurbish that satellite and go again. And part of the business model here is that simply launch costs are dropping dramatically, which is making so many of these commercial activities become more palatable, shall we say. So as part of that deorbit, controlled deorbit technology, we've also been trialing heat shield in a microgravity environment. So this was a heat shield prototype on board a parabolic flight, opening out. So it's essentially like a Mary Poppins umbrella, opens up, slows down the satellite, brings it through the Earth's atmosphere, and then gently floats back down to Earth. So that's a big focus on the satellite and the space-based activity. But there's also then, okay, why and what is it that we're aiming to achieve? So we're by no means the first to look at this. Over 50 years, back in 1973 on the Skylab, was some of the first early experiments done on semiconductor crystal growth in space. So there's a whole database of over 163 materials that have been looked at over 50 years by the state funded space agencies, Russian, Chinese, Japan, ESA, USA. There's a peak there where the space shuttle was regularly going up and conducting experiments on its wake shield. It's dropped off a little bit, even though we've got the International Space Station. The International Space Station is nearing the end of its life. And I think that when it comes to actually looking at doing semiconductor material growth in earnest, some of the precursor materials are quite toxic, and the ISS is quite a contained, sort of sealed environment for humans, and the two probably don't mix too well. So we're having to come up with other solutions and other ways around. And what I want to really highlight here is a lot of these are one-off experiments. So Anne Wilson at the University of Butler University, she was able to get hold of quite a substantive amount of data and research outputs from a lot of those experiments. And she did a meta-study. And she was looking at 4 key metrics to look at what the effect of microgravity was on that crystal growth. So do the crystal grains grow larger? I would say purity, defectivity levels, and also say what the performance is of any material, any devices, or however they're deployed, the materials, is it any better? And so across 140 materials that she got hold of data on, over 85% showed improvement in at least one of those 4 metrics. I think there was one experiment whereby I think it was the Chinese space agency actually looked at a device fabricated. And it's hard to quantify without the data, but there was a simple statement that was thrown in there that there was marked improvements in device performance. So in terms of what's enabling this and what's particular about the microgravity environment, say, for example, if you've got a chamber that you're creating your semiconductor crystals in, you can have precursor materials. For us, it's precursor gases. They have different masses. Within the Earth-based environment, you'll get some, say, sedimentation is the best way I can think to describe it, where you've got the heavier molecules sinking and the light ones float up to the top. In space, you don't have any of that. There's no gravity causing that to happen. So the theory is that there's a lot better mixing. Anyone designing a satellite knows how difficult thermal management is. There's no convection in space. Within a chamber, growing these crystals with the precursor gases, you've got no convection. So again, better mixing of the precursor gases tend to lead to, shall we say, better crystal growth, orders of magnitude lower defectivity levels, and higher purity materials. So what we're aiming to do is produce superior crystals compared to Earth. And it really is just focusing on what space can do and is needed to do. So, for example, seed crystals. We're not necessarily looking at growing ingots. I think that whenever we talk about, say, manufacturing of semiconductors in space, people instantly think about chips. And it's no, it's the semiconductor materials that we're looking at. Generally, the aim is that these materials, when brought back to Earth, deployed in terrestrial applications, can lead to major environmental benefits in terms of being able to realize devices that are potentially way more reliable and more power efficient. So our first material that we're working on is diamond. And there's certain reasons for that in terms of some of the precursors. being relatively simple precursors, shall we say. And there's different ways of creating diamond. There's the natural process, which we can't really do in space. High pressure, high temperature. Probably also means high power. Detonation's not really going to work well for us. So we're doing microwave plasma enhanced CVD diamond growth. And this is a process which really, shall we say, cheats nature. It allows us to grow semiconductor grade diamond at relatively low power levels. And when trying to deploy these sort of systems in space on board a satellite, you can imagine that, yeah, we have to be careful with our power budget. So in terms of what our activities are, I've mentioned that there's all those experiments. I think that where we're at is actually, how do we take this into something that's more of a production? So we're in the process of doing diamond growth in Swansea. Yeah, less glamorous than space, but yes. But that is partly, we have to do the benchmarking. We have to understand how the materials grow, what power levels we can operate at, that then influences the payload design, influences the satellite design. And as much as anything else, there's so many efficiencies that we need to consider making. Gas usage, power, cooling. So that's getting a churn, shall we say, of terrestrial growth, whether that's with a tool that we've purchased off the shelf, or then a satellite payload tool that we've developed. So we have to do that benchmarking. And as much as anything else, with that satellite payload tool, doing the growth in a terrestrial environment allows us to intuitively know what is going on within that chamber, such that when it's up in low Earth orbit and you've got the tiniest of windows in which to communicate with the satellite, we can respond very, very quickly to making tweaks and changes to air growth conditions. And as anyone knows, with semiconductors, it's about optimizing the process, doing these experiments again and again and again, and building up the data sets. And that's what we also have to consider when we move forward. So where we're currently at, we've moved into CISM, a state-of-the-art facility at Swansea University, where we're establishing a terrestrial diamond growth capability and post-processing, so they can be integrated with terrestrial applications. As much as this is, I think that you can probably appreciate that there's timescales involved with what we're doing. There's a huge amount of risk with what we're doing in terms of the materials, in terms of where they come back, how good will they actually be, but also how will they differ to terrestrial ones, and will people want to play with them and explore them? And we have to build up those relationships now. And so that leads me on to, I guess, why I'm here. With a background in RF and telecoms, one of their sort of use cases is that, well, telecoms sector uses semiconductors, if you didn't know. And we're aware that, you know, diamond has got really great thermal management properties. There's different ways of integrating that. Say with gallium nitride devices, can either look at it doing it at the die level packaging or at the wafer level. So wafer level, GaN on diamond goes through a fab, comes out the other end with a device on it. Sounds simple. Diamond doesn't actually like to play with any other materials. Certainly from a thermal management perspective, there's a lot of interface engineering science that needs to be done. Diamond conducts heat via phonons. Other materials conduct heat with electrons. They don't match up or marry too well. But if you can get it to integrate, regardless of which way, die level or wafer, if you can get it integrated and get the heat away from the gate and the channel, you can massively improve the reliability of these devices. What I've tried to show here is, yeah, that's one application that's relevant here of diamond. Longer term for us, it's more down to, okay, the quality of the semiconductor chip material. Removing defects and impurities, again, could probably improve that device performance, reduce its operating temperature, and not even require that diamond heat spreader. But that's long way off. But that's essentially where we're aiming at. We're aiming at being able to produce these materials that operate more efficiently at lower temperatures and higher power densities. So you can massively reduce the size of those devices. When it comes to the heat spreading and removing the heat away from the chip, from the channel on a, say, a GaN device, I think it was Chris who was mentioning FR1 bands. We've been involved in a project where we've been looking at the FR2 band, so up at 26, 28 gigahertz. And the end user, the operator, is BT. They know that these base stations are going to be deployed upon, say, buildings. They can't afford for the air conditioning units and all the power associated with them to be mounted upon those buildings. They need something at the chip level, particularly as we move to, say, massive MIMO, where you've got a higher density of amplifiers all on the one chip, concentrating heat and needing that heat to be dramatically extracted. And they see it being done at the chip level as being critical to them being able to deploy and roll out these base stations for millimeter wave FR2. In terms of the benefits of GaN on diamond, I think there's quite a fair few sort of papers out there just in terms of highlighting how you can get that higher power density, how you can reduce those the channel temperatures with the dissipated power, how significantly you can improve the reliability of those devices, reduce their size and increase their power efficiency. So as much as anything else, that's the broad overview of why we're doing the first material and where we're working with certain partners to look at realizing some of these benefits. In terms of next steps, yeah, we're in the process, like I say, of moving into SISM and looking at how we do actually improve the growth within certain constraints that the space environment will impose upon us. So power, weight, size that you'd expect any payload to struggle with going onto a satellite. And then ultimately, you know, not necessarily just diamond, but broader speaking, the other materials that we're starting to look at. These are the sort of sectors that we're looking at, power electronics, RF microwave. We'll work with people working on the diamond-based devices, and of course, quantum also falls within that. So yeah, whistle stop tour in terms of what we're doing. Probably missed a fair bit out. Hopefully you found it interesting, and I'll open it up for any questions.
Thank you very much, Darren. I'm sure there are lots of questions after that. Very interesting talk. Yep.
Thank you very much, Hasha from MediaTek. So if you are using LEO, so the acceleration and the velocity of the station, and probably the thermal management of that because it's going around the Earth, right? Would that have any effect on this crystal realization?
On the crystal orientation?
Yeah, in the whole thing, will it affect any jittering of this process?
I think the flippant answer is we've got to find out. And I think that's one of the things which is probably exciting. We just don't know. Again, until we start doing those growth experiments, getting the materials back. You could even argue, does it make any difference whether we're at 500 kilometers or 600 kilometers in terms of altitude? We just don't know yet. Sorry, really vague, but yeah, there's a scientific endeavor that is required, and scientific rigor, to say.
Liam?
Hi, Darren. Just a logistical question for my personal interest.
Yeah.
When you launched your satellite, did you take out an insurance policy in the event of catastrophe?
Which one? So the first one, I hadn't joined. So the one in January 2023, I think that because it wasn't our fault, there was insurance associated with it. I think though that also we got so much publicity from it as well that sort of also compensated. I mean, I think the in terms of the satellite more broadly and using the one that didn't come down, I think that went into the sea. It's something that I've not really covered, and it is really that it's not just the regulation in terms of anything returning to Earth. It's also for us, if we're setting up a business, you're right to mention America. We've launched the satellite over in America. We've made the satellite in the UK. It's going to go up in space and land maybe, say, in Europe. Where were the products made? What's the export-import licenses associated? There's a bit of space law that we've got to wade through. Yeah.
That's right. I've got I've got one just quickly. I know this is a how long is a piece of string question. Do you have any idea when you will get usable materials for production from?
For me, I'm always more on the it'll take a lot longer than we actually think. There's ways that we think that we might be able to get early results, say, from certain experiments that we can do. Will they produce enough material to become actually seed wafers? Probably not, but we can get a feel. I think that there's so many different technologies that we still need to prove, and not just ourselves. So like the satellite return technologies, there's companies out there such as VADA and Atmos also developing return technologies. But again, not 100% proven. VADA have done well, they've returned satellites, but there's that whole sort of package of not just making something up there, but also returning it and in a controlled way.
Yeah.
So really vague. Sorry, it's going.
That's what I was expecting.
yeah.
I just thought I'd ask it anyway.
I think it's the timescales with, just say any semiconductor process development, semiconductor device process through to acceptance, through to production. It's not a quick timescale.
I think there's an element as well that if you're, if someone starts doing it, it generates its own impetus, and others will join in and help.
We are starting to see some competitors emerge, but I think it's also a case of we've chosen one material. Some of the other competitors will choose a different material, and we don't know actually which material is going to make real commercial sense to be made in that environment.
That's very exciting anyway. Sorry, you asked.
That's okay. Hi, I'm Paul Hickling from Radio Design. I apologise if I missed this in your presentation, but with the satellite that you've just launched, was there the capability to grow a crystal on that satellite, or was it just testing the re-entry mechanisms?
So we're not testing the re-entry system fully on that one. The satellite will burn up in the outer atmosphere. Okay. In terms of the payload, the growth tool, that's got various commissioning and scientific experiments, won't involve growth.
Okay, thank you.
Okay, we'll move on to the next speaker then. Thank you very much.
Thanks, Helen. Thanks, everyone.